Hello and welcome back to another update of my 14-cylinder home-built engine here. Things are getting more exciting now because it's getting very close to being started up. But I thought we would run through a more detailed look at the motor so you understand more about what's going on and how it was made, and just, you know, a better overview so you understand the motor. But before we do that, I have some subscribers, and these people have been hanging on for months waiting for information. They're genuinely interested in the engine and I'd like to thank them. And the first one is Marty B. There's another one, Silvio Concalves. Now, sorry Silvio if that's not quite right. Winston Larrison, Tigrell, Michael Fisher and Gerald Stewart. Now these people, you know, obviously very interested in the motor and I appreciate it, so I just wanted to tell you that you know, I appreciate that. And so now let's get on and have a look at what's going on here. So we'll start with the whirlwind prop. This is from America, and it's an airboat prop for pushing like a swamp boat, that kind of thing. It's a mean bit of gear, because this propeller will absorb from 400 horsepower to 700 horsepower. And it's adjustable, so by loosening the hub bolts you can pitch this blade up or down. So there's three scales on the propeller. There's an A scale, a B scale and a C scale. The A is for belt drive, the B is for direct drive, and this engine is a direct prop drive straight on from the crankshaft straight onto the propeller. And the C scale is for the gearboxes, a gearbox drive. And so Whirlwind have told me to start with a pitch angle on the B scale for direct drive at 10 degrees. And you can't see in here, but there's a scale on the hub and you've got the ABC on the blade, and you just line these up. And the idea being when we're starting to tune this engine later on, we can keep pitching the prop up, absorbing more and more power until the engine gets sick of it. Mostly this prop is 2700 RPM governed, so we can't go over 2700 RPM. And I'm hoping maybe for around 600 horsepower or something like that, but we'll get into that later as to why. So that's the story here. It's not like an aeroplane propeller. It's got a very thick cord here. And it's the low speed area of the blade. It's doing lower, same RPM but lower linear speed, and these are designed to do a lot of work, whereas on aircraft propellers out here the tip does all the work. The tips do most of the work on aircraft propellers, so these are quite different. And this is a very mean bit of gear, and if we're making the horsepower, we make the thrust. And Whirlwind say that you make 4 pounds of thrust for every horsepower. So if we end up getting 600 out of this, 6 fours are 24, that's 2,400 pounds of thrust, which is an imperial ton. Sorry about the imperial business, I don't do metric. So that's huge. So we'll see what happens. Okay, so that's the propeller. You know it's going to be direct drive. So this is one half. We'll come over here a bit. This is one half of the drive hub, which will be hooking up to the propeller when the shaft is made. And there's a laminate between these two, and that is to insulate the prop from the crankshaft, because they can be pretty hard on props. So we're putting this in as a bit of a safeguard and a bit of insulation so that they don't interfere too much with one another. Now the whole engine is based on the XV1700 Warrior. Now this is the crankcase. Now on here there's actually Silverado barrel and heads. Now it's the same, the Warrior and the Silverado are the same, but there are differences in the barrels and the heads. And I put this on here just to show you the difference as to why I've used Warrior barrels and heads and not the Silverado. So to start with, the Silverado is a higher performance motor in the rev range. It's got this massive inlet port, But conversely, the Warrior cylinder head port is like a strangled duck, because this motor is a muscle engine that's designed to have high torque at low RPM, and we have a low RPM engine here, so this is good, and we can turbocharge successfully at 10 psi through here. So you can see that it's got a very deep chamber, pent head configuration. The engine only runs 8.3 to 1 compression, and this makes it ripe for boosting to get more potential out of the engine. Really, I think this motor would only make 350 horsepower if it had been left at naturally aspirated, which is pathetic for a 12 litre engine. So that's the reason. Oh, the other reason too is that this exhaust port is facing front, and it would have looked pretty awful, I think, whereas on the Warrior they are inboard, and you can see on the engine here that I'll be able to sweep them around and take them back instead of them coming, you know, all the way out here and trying to get them around. And I think aesthetically that makes the engine look a lot better. The other thing about it is that the cylinder fins on the Silverado motor are much smaller. The fins on the Warrior are much deeper, and with the different shaped head here, if you look at the motor, you can see that the cylinder heads and the barrels integrate much nicer. They look nicer, and also fills up the gaps between the cylinders, and I think it really looks good because there's not much in the way of air gaps in it. The engine's, you know, really full, and it looks a bit of a brute. So that's another reason why I chose the Warrior heads. And yeah, I think the result's pretty good. So a bit of work in figuring out how to big to make the crankshaft, because it's the old problem. If you're trying to make something out of something that was made for something else, it's not that easy. So I wanted the engine short, and so to get the cylinders in like this, I had to trim some of the fins in non-critical areas, as it turns out, to compress the engine up and get that compact, no air gaps look, which I'm very pleased with. It's worked out really well. So next thing I was going to talk about is the cams. Now, most of you will know that cams work a bit differently in radial engines. This is the standard cam, or one of them. They have two because of the rear cylinder and the front cylinder. But these cams are very good for torque. They don't have much overlap. You know, wilder cams, these two lobes get closer and closer together, and the overlap grows for heavier breathing at high RPM. You don't want overlap, a lot of overlap with a turbocharged engine, because you want to keep the manifold pressure up, and if you're keeping the valves open too long, you're just losing air pressure. So these cams have been what's called clocked, and they're put into a jig, and there's a DDI gauge put on, and they're turned incrementally, and the shape of the cams are then plotted, and you do each one. One's an inlet, one's the exhaust, and then that profile is then put onto the cam ring, and this is the cam ring, and you can see that there's two bumps because there's two tracks, one for the inlet, one for the exhaust. And so you can see the overlap here in the same way that if you look down the cam, you can see the overlap there. This lobe here and this here, that's where both valves are open at the same time. And so that profile is then put onto your own cam plate, and this cam runs at 1/6 speed backwards. Now the formula is just brilliant because you can actually run the cam forward as well, and the formula is very simple because the ratio for the cam plate is the number of cylinders on a row, in this case 7, minus 1, which is 6. Now that 6 determines the ratio or the speed of the cam plate, which is 1/6 speed backwards. And if you divide the 6 by 2, you end up with 3, so you have 3 lobes on each track. you can do it another way. You can have the 7 cylinders plus 1, which is 8, and the speed is 1/8 speed forward. And if you divide the 8 by 2, you end up with 4, and so you have 4 lobes on each track and not 3. And you know, it works in exactly the same way. Now it works perfectly. I was going to do this on this engine running 1/8 speed forward because it's not the norm. Most 7-cylinder engines run the 1/6 speed backwards, but it was too hard to get the gear train into the case. It's much more complicated to get that the forward direction, and need more gears, and because there's too much. So ended up going back to 1/6 speed backwards with 3 lobes, and that's pretty standard for 7-cylinder engines. If you want to know more about this sort of thing and how it works, there's a guy on the YouTube channel, and my computer broke down, but I think if you put in working wood model of a 9-cylinder radial engine, I think the YouTube will find it, and you'll get a absolute first-class explanation of a 9-cylinder and the cam operation, and it's perfect, and you won't have any doubts as to what's going on inside these engines if you watch that program. So that's a good idea. Now, moving up from in the crankcase, these are LS1 V8 GM type lifters, and they're a roller lifter. In the standard engine, of course, they don't have to be, because the lifters just run on these. But of course, with a turning track like this, they have to be a roller hydraulic lifter. And inside the crankcase, you've got the housings which support these, and then this plate goes on over the flats of the lifter, and this keeps each lifter straight, so it runs on the track. And then these standard housings, I've cut them down from that length down to just 1 O-ring. That pops in on top like that and bolted into my own crankcase, and this enables you to put the pushrod tube and everything back on in the standard way from the motorcycle engine. On the top here, it's just a very simple arrangement on the top. It's just 2 rocker shafts and 2 arms on each rocker shaft to actuate the valve and the push rods in there. So it's very simple, and these shafts here get lubricated by oil being pumped up from the lifter through the hollow push rod tubes, and they come up in here, and then that oil migrates down through the shafts to keep them lubricated. So actually, there's on the motorcycle there are 2 jets, one in here, one in here, and they were there to pump, so the oil pressure could pump up to the top here and spread oil around and cool the cylinder head. And that oil would then run down back through these 2 holes in the back of the cylinder head here, back to the crankcase. Well, that becomes impossible on my engine because the cylinders are upside down. So those oil lines up to the cylinder heads are not on this engine. I did put them in, but I thought there might be too much oil going to the top, and we don't need oil cooling for the cylinder heads on this engine, because with the prop going all the time, there's enormous draft across the engine, and so we don't really need all that oil going up there to cool the heads. The other problem too is with more oil, more problems getting the oil out of the rocket areas, and I was very limited as to what I could do to get that oil down. And so I've got fittings screwed into the sides of the heads here, and hoses coming down one to the other all the way down to the bottom tank there to try and get the oil out. Yeah, I'm hoping that'll work. It's a bit tricky, but the oil return system from the engine is going to utilise a pressurised crankcase. There's no breather on the crankcase at all, and the crankcase pressure builds up and it'll drive the oil back to the tank. And you'll notice I've got this dog leg down the bottom here, and that's so oil sits in the bottom, and it'll take a certain amount of pressure to push the oil back and into the tank. Now that internal crankcase pressure is going to help drive the oil out of all the valve covers and down to the lowest point of pressure, which is down the bottom there. So that's the theory. Rotax, I think, do it with one of their aero engines, their flat fours. They push the oil back to the oil tank using crankcase pressure. And to see what's going on with the crankcase pressure, I've just made up this what's called a manometer, and it'll plug onto effectively the crankcase down here. And as the crankcase pressure rises, you can see the water rising. And if I can see how many inches of water I've got, then I can work out what the crankcase pressure is, and I can look in the window of this oil tank here, and if that's basically staying clear, then I know I'm getting the oil back to the tank. So that's what I'm hoping, and that's how I'm hoping the system will work. We'll see. You know, I don't know what the contingency plans will be if it doesn't, but we'll have to dream up something. Now, these cylinder heads on this engine are twin plug, unfortunately, so it required 28 coils to you know, fire all these plugs. So these coils are sitting here as they're bolted on, and I must say they look all right. I'm pleased with them really, because all the late model Radial engines that had the low tension type ignition system like these had the coils mounted on the heads. So I think it makes the engine look more purposeful. I've got one of the plugs out of all of the cylinders at the moment to make it easier to turn over when I'm working on the oil system. But I'm quite pleased with it. The intake system, there's 7 branch arms off the plenum at the back. They turn into a Y and feeding 2 cylinders. Incidentally, the front cylinder off the motorcycle is on the front, and the rear cylinder is turned around and is on the back. So and I worked it that way so that I could come up with 1 branch arm off the plenum chamber and then split it and go into 2 cylinders. So that's how that works, and I think it'll be all right. The injectors are good for 50 horsepower, and I'm looking at probably 44 per cylinder. So these Bosch type injectors should fit the bill, and we should be well within their working range as far as duty cycles and that sort of thing's called. So you've got to be careful with that, but it's not a high revving engine, so that should be good. Now, as far as the horsepower is concerned, if you look on dyno graphs of this particular motorcycle, the XV1700, you'll see, if you find any on the internet, you'll see that these cylinders are making about 25 horsepower at 2700 RPM. So that's like 50 horsepower at 2700 RPM, because you've got 2 cylinders. So splitting that, but also that horsepower is measured at the rear wheel. So you can add maybe 10% to that to compensate for the losses through the transmission and final drives. So I'm sort of working on the 25 to 27 horsepower range, and the turbocharger we're putting in 10 pounds, which is basically 2/3 of 1 atmosphere. So if you've got, say, 25 horsepower and you put in, you know, 10 pounds of boost, you're up over 40 horsepower, about 42, 44 maybe. And that would deliver, you know, 580 in the 600, 615 range, depending on how it goes. So that's sort of what I'm working on as far as the power delivery. Because if you add 1 atmosphere to a cylinder that's, you know, making, say, 25 horsepower, and you add 1 atmosphere, you'll get double the horsepower. That's theoretical. It doesn't include the losses and friction and all that sort of thing, but that's basically how it works. So by putting in 60% or so, you know, it's quite a big increase, and it's very safe on this engine, because as you can see, the chambers are really big, and it runs only 8.3 to 1 compression. So I can just run ordinary pump fuel in, probably 95 or 98 if it's available, and it should be a very, very safe operation without any getting into detonation and that kind of thing. So the engine, as far as the way it works with the crankshaft and whatnot, it's a 180-degree throw crankshaft. So if you can imagine a flat twin like a BMW 1200 or something like that, you know, you've got the pistons going in and out like that. Well, that's exactly the same as what's happening here. The number 1 and the number 8 cylinders are the pistons at TDC at the same time. Now the cylinders are numbered from the back to the front alternately. So the back top one is number 1, and because the engine rotates left hand, this is number 2, that's number 3, 4, 5, and all the way around. So the firing order is actually 1, 10, 5, 14, and it just keeps following that pattern all the way around. Now because it's a 14 cylinder and there's only 7 cylinders on each row, I don't need to have 2 computers, which was what was thought in the first place, but you only need 7 channels because both pistons are at TDC on number 1 and 8 at the same time. Either one or the other is going to be firing, and the other one's just TDC overlap. So you run a dead spark, the same as what a huge number of engines do. So both, all 4 coils fire at the same time. 2 on this bank, 2 on that one, and you only need 7 channels to do that because you're only essentially firing, you know, it's only 7 cylinders on each bank. So I hope that is clear. Also with the fueling, you can fuel onto 2 banks at the same time because the firing interval on this engine is only 51 degrees. So there are always 2 cylinders well into the intake cycle at any time. So both those cylinders can be injected into. So 1 and 8 would have been injected too, but the cylinders that are coming up to fire in the next rotation, they'll be injected at the same time. So again, you only need 7 channels because you're injecting both banks at the same time. So the computer is a Motec M150, quite a high-tech thing, and that's how this engine is going to be run with one of those. And I've had a lot of help from a guy called Mark McCoy in Australia. He's a Motec guru, and he's given me an awful lot of information and help to make the wiring loom for this engine, because that's been quite complicated for me when I hadn't done it before. And when you've got to do 28 coils, it's quite a mission. But you end up being given a big printout sheet like this with all the different components all the way down here, and then a pin number on this side. And so it becomes quite easy to make your wiring and matching a pin number to a component, and you just work your way through it. And I found that in the end I was, you know, getting less stressed about it, and it worked out quite well, I hope, because we haven't started it yet. So moving around to the back of the motor, we've got, we've got a Canadian CRV starter here as 1.9 horsepower with a 4-to-1 reduction. Now I don't think it's really quite big enough, but we'll see. But there is a 3 horsepower one available, and if this one's not up to it, well, we'll have to change it. But if the engine starts fairly quickly, then it's not going to get too hot. But if it labours to start, well, then something might have to be done. It's driving a ring gear off an XD Falcon auto transmission type, and the flex plate was cut out of the ring gear, and then the ring gear was welded onto a new steel flywheel section here. So that's easy enough. And then if you come around this side, we've got the alternator mounted here, which is a industrial type, so it should have really strong bearings and things. It was a V-belt drive, but I converted it to a 4KP micro belt because I like the look of them better, and there's not going to be a lot of load on it because it really only has to charge the battery and run the ECU, so that should be more than satisfactory. On here we've got the timing speed sensor. So this is what's called a 36-2, but in fact it's only got 1 tooth missing instead of 2 because it's quite big, and the angle here is going to be big enough for it to, the computer to work out the starting, because this is really important for starting. So the guy that made the starter bracket, very thoughtfully put a little lug on here, and been able to put the speed sensor here, and that's, you know, really tidy, and I'm very happy with it. Looks really good. Down here we've got an LS1 5.7 litre throttle body, same engine as what the lifters are coming out of. It's come over here, it's got a 75mm throttle body, and and some people think, well, that is not very big, but even though the engine's 12 litres, the CFM, the amount of air it uses every minute, is actually quite low because it's not a high RPM. So this would run the engine naturally aspirated, let alone been forcing huge amounts of air through it for boosting. And also on here, there's a 4-wire IAC valve, air ratio control valve, anyway, for us keeping the engine speed. They're too complicated to tune, so on here I've put on a Falcon 2-wire IAC, inlet air control valve, that's it. So I put on a Ford one with only 2-wire, and that's much easier to tune with on the computer. So that's another little change. Now the turbocharger, which is right here, this is purpose built by a crowd in Christchurch in South Island, New Zealand, called TurboCare. And this is, I gave them as much information about the engine and the size of the chambers, the ports and everything else. And they've come up with this purpose-built Borg water turbocharger. Now this should answer to the prop very quickly. As soon as the prop wants to turn, the it's going to demand fuel, and the hotter exhaust gases should be getting right into that and speeding it up and getting us underway really quickly. The size of the plenum chamber is probably about 11 litres, which is really 11 or 12, which is only the same size as the engine. Most engines out there have the plenums are at least twice the size of the engine capacity, but that would be monstrous on this motor. So the way this engine is going to be run is there's no throttle standing. In fact, you won't just be whacking the throttle open and then having the plenum chamber being emptied by the sudden increase in piston speed. So this will be throttled gently because it's an airboat motor. So you select the power setting and then gently move it to another setting. And so for that reason, we don't need a really big plenum, because the turbo will be able to keep up with that and keep it filled. So that's the story there. I'll just show you inside this box so you can see the ECU. So that's an N150 box there, and I put a lot of relays in because there's so many coils. I'm just a bit old-fashioned. I don't think I really needed them, but I put them in just so that to carry the load of this 28 coils. So yeah, it's just one of those things. I hope it all works, because I'm not a Sparky, but we'll see. So that's where we're at really, and once I get more testing done on the oil system and I'm satisfied that it's all going to work, then I'll be ringing and contacting Mark McCoy in Queensland, Australia. And it's one of these things you can do these days. He will start this engine from Australia. So we'll be putting in a device here to talk to the Sky, and he will configure the ECU to be able to start the motor. Now if that's successful and it runs okay and we can idle it, won't have the prop on, idle it, and it's basically functioning in that way, then we can safely move to the next step, and that is when the shaft has been built to put the prop on, I will fly Mark over from Australia and we'll spend time tuning it. And like I was explaining before, we can pitch the prop so we can run through. If the engine's still laughing at the prop and saying, well, you'll need more than that, we can keep putting it on until we get the engine topping out on the throttle plate here and have the throttle wide open and it won't pull anymore, and then we know we're at the limit, and then we'll give it a little bit of margin and pull it back a bit, and then I can ring Whirlwind in the States and say, well, we ended up with this pitch B15 or something. whatever it is, and they will come back and say it's making this much horsepower, and it's very accurate. So that's where we're going to be in the next coming, well, hopefully in the next coming months. And I'll be doing another video of when we actually do the initial start. That'll be scary, but I'm going to do that one for you, so you can see it actually start the first time, if it will. And then we'll do another video when we're doing the tuning and see how that goes. So I hope that's a reasonable explanation of what's been going on and how the engine works and what's going on. And I look forward to catching up with you again in the next step, which will be, you know, hopefully getting it to go. And I look forward to that. So ciao for now. See you.